Hi everyone, the topic for this video is displacement in one dimension. We'll cover displacement in two dimensions in another video. Displacement is the description of the position of an object relative to some reference point. That reference point might be another object, or it might be where the object in question started. Displacement is a vector and includes both magnitude, which I'll say is a distance, and direction. I'll talk about those in a little bit. And the two rules for relative displacement are xb relative to a equals negative xa relative to b, and xa relative to c is equal to xa relative to b plus xb relative to c. I'll explain why those are intuitive and how you can use them, and I hope that you find by the end of this video that they're actually pretty handy. Net displacement is the final displacement minus the initial displacement. Delta x, this is not delta times x, we actually just read it as delta x, equals x final minus x initial. So, what is displacement? I've actually struggled with this question a fair amount. I think that a lot of the definitions that you see are going to be kind of circular reasoning, so this was what I came up with. Displacement is a detailed description of the position of an object relative to a reference point, or two objects relative to each other. The reference point oftentimes is where the object started. It could be arbitrary, it could be, on the moon or something like that. But displacement is a vector quantity, which means it includes both a magnitude, which is a distance, and a direction. Note the color coding here, because we're about to use it. Examples of displacements include 10 miles directly east of the capital, so this is expressed as a phrase, it's not a mathematical construct or anything. 10 miles directly east of the capital, 4.5 inches left of my coffee cup, and 200 meters above the school library. And so go ahead and compare that with the color coding from before, and you'll see that each displacement includes a magnitude, a direction, and a reference location. So 10 miles, magnitude, east, direction, and the capital for the first example is my reference point. Displacement and distance, or displacement versus distance. Displacement is not the same as distance. Distance does not carry information about direction and only increases through travel. This forms the basis of many trick questions on standardized tests, so be on the lookout for that. For example, if I walk 2 kilometers east and then 2 kilometers west, my distance traveled is 4 kilometers, but my displacement is 0 from my starting point because I end up back where I started. As a non-trivial example where it doesn't end up with a final displacement of 0, if I walk 3 kilometers east and then 2 kilometers west, then my net displacement is 1 kilometer east, while my distance traveled would be 5 kilometers. And I have to be honest with you, I occasionally will slip up and say distance when I really mean displacement. I really should be better about it. I will try my best. Call me out on it if I do make a mistake, but most of the time I mean displacement, because physicists really care a lot more about displacement than they do about distance. Okay, let's talk about direction. Direction is often just stated outright. For example, left, right, above, below, north, south, east, west, in front of, and behind. That's often how it's given to you in a problem statement, is they'll tell you the direction just through words. But we can also indicate direction by drawing a coordinate system and specifying positive axes. So I've highlighted this in red, and that's because I'm going to, throughout the semester, draw most of my coordinate systems in red. So for example, if my displacement is 30 meters south of my home, then I can draw a coordinate system that looks like this. And let's specify that the positive north direction is upward on this coordinate system. You note that I can omit the horizontal axis because the problem statement, or this statement right here, doesn't include any information about an east-west component, and so I'm just drawing the north-south axis. And then we can write x, my displacement, is negative 30 meters. And because I have both the coordinate system and the negative sign in front of the 30 meters, it's unambiguous that I mean 30 meters below the origin, taking north to be positive, so 30 meters south. Negative 30 meters north means 30 meters south. And it gives all the same information as if I had said 30 meters south or negative 30 meters north. So an alternative way of doing this, and I encourage you to be creative as you do physics problems, is we can draw, again, north-south coordinate axis, but specify the positive south direction is downward. And we don't draw in the north direction because we don't want two positive quantities on the same axis. And then we would write, for this version, x, our displacement, is equal to positive 30 meters. And that, again, carries all the same information that we would have if we use that coordinate system and x equals negative 30 meters. So let's talk about the first rule of relative displacement. I'm going to lead by example. I'm not going to talk about it first. You'll see that it's pretty intuitive through the example. Alice is 20 feet to the right of Bob, and my question is, what is Bob's displacement relative to Alice? Very simple question. Here's Alice, labeled with an A, and here's Bob over here. You can see that she is in fact 20 feet to the right of Bob, and I've gone ahead and specified the coordinate axes for this problem. So in advance I've written the coordinate axes, and I say that positive values of x indicate displacements to the right. Okay, so we can write x, A, and a vertical bar, and B, and we read that as XA relative to B. So I'll make that a little more clear in just a second, is equal to 20 feet, or positive 20 feet. Okay, so again, the vertical bar means relative to. So you write XA relative to B equals 20 feet. Let's check that that's true. Positive values are to the right, and Alice relative to Bob, or A relative to B, is positive 20 feet. So that means that Alice is 20 feet to the right of Bob. Okay, so the question was, what is Bob's displacement relative to Alice? From the diagram, just by looking at this diagram, it's apparent that Bob's displacement relative to Alice is 20 feet to the left. So x b relative to A. By the way, I'm putting a vector sign over all of my x quantities to emphasize that they're displacements. That's not so crucial at this point, but I'd like you to know that displacement is a vector. So Bob relative to Alice is 20 feet to the left, or negative 20 feet to the right, or just negative 20 feet according to the coordinate system that we're using. This specific result is not what I want you to take from this page. What I want you to take from it is that xb relative to A compared to xa relative to B. Can you guess what the general rule is? I think you probably can. So no points for guessing. You're correct. xb relative to A is equal to negative xa relative to B. And that's it. This is a general rule. If we have other people involved, then we can use the same rule to find all of their relative displacements relative to each other. Okay. I'll show you what that looks like in a little bit. First, let's talk about the second rule of relative displacement. Alice is 30 feet to the right of Bob. Bob is 50 feet to the right of Carl. What is Alice's displacement relative to Carl? Again, I've specified that positive values of x correspond to positive displacements to the right. And Alice is in fact 30 feet to the right of Bob. Bob is 50 feet to the right of Carl. Okay. Sorry, I'll continue this on the next page. And what we do is we write XA relative to B, Alice relative to Bob, is equal to 30 feet. Right? And XB, Bob, relative to Carl, is 50 feet. All right. Again, I'd like you to look at the diagram, and just from this diagram, what is Alice's displacement relative to Carl? So take a moment, pause the video maybe, but I think you can figure out that Alice's displacement relative to Carl from the diagram is 80 feet. Look, here's Alice. Oops. Here's Alice. She's 30 feet plus 50 feet to the right of Carl, and so her displacement relative to Carl is 80 feet. In general, how did we get that result? Well, we added these two quantities, and in general, what you'll find is XA relative to C is equal to XA relative to B plus XB relative to C. All right. Now, if you want to remember this rule and know how it's applied, you should realize that it's elegant, or at least I think it's really elegant. I like it a lot, because the B's will quote-unquote cancel. So X A relative to C, I'm just going to rewrite the rule, is equal to X A relative to B plus X B relative to C. And then look at this. We have B on the right side of the first term and on the left side of the second term. They're right next to each other. They're begging to cancel. And if you want, this is how I sort of think about it. They cancel and all of this gets erased. And then the C comes and hangs out with the A, just like we have on the left-hand side. But what you should really know is that they cancel because they're next to each other in the subscripts. You have B on the right of the subscript on the left, and B on the left of the subscript on the right. And this can be done as many times as needed. You can actually just prove this by repeated application of this rule. So this is not something that I'm just telling you. You can prove it mathematically by using this rule multiple times. Suppose we have not Alice and Bob and Carl, but like A, B, C, D, and E. XA relative to E is equal to XA relative to B plus XB relative to C plus XC relative to D plus XD relative to E. That's D relative to E, not die there. Okay. And the B's cancel because they're next to each other. The C's cancel because they're next to each other. And the D's cancel because they're next to each other. And we're left with X, as we were trying to find earlier. We wanted A relative to E, and we canceled everything else, and so we have A relative to E once our cancellation is done. So that's what we want to see on both sides. So the two rules can be applied together to problems that are otherwise difficult to diagram. Especially in 2 dimensions, but we'll just do some 1-dimensional problems for now. So, I love these kinds of problems. I will just say there's a decent chance that you might see one on the exam. Diana is 13 feet to the right of Carl. Bob is 5 feet to the left of Alice. Diana is 7 feet to the left of Edward. Carl is 2 feet to the right of Bob. And what is Alice's displacement relative to Edward? I think you have the information that you need to solve this on your own, so I would suggest pausing the video and trying to solve it on your own. But here's what I do. I'm going to first begin by specifying my coordinate system. I'll say that positive x values are to the right. And we know a bunch of information. Let me try and get it all down. X Diana relative to Carl is positive 13 feet. X Bob relative to Alice is negative 5 feet. x Diana relative to Edward, which is not die, is -7 feet. And I'll squeeze it in down here. X Carl relative to Bob is equal to 2 feet. Okay, so go ahead and look through all of these I've written down and make sure that they correspond to the terms that you see in the problem statement, and I've done this correctly. Those are the quantities that I have. So let's first write x. We're asked for Alice's displacement relative to Edward, xa relative to E, and that's equal to xa relative to B plus xb relative to C plus xc relative to D plus xd relative to E. What is that? That's the second rule. It's just this version of the second rule where I've written it out with 4 terms on the right-hand side. So this is just an application of the second rule. Do we have these terms? No, we don't have these terms. We have some of them with their subscripts flipped. So for example, we don't have xa relative to B, we have xb relative to A. So you have to be very careful about how we apply it. So we apply the first rule to the individual terms, and what we get is xa relative to E is equal to xa relative to B, but we're not given that, we're given -xb relative to A. That allows us to swap the order of the subscripts by putting a negative sign in front. xb relative to C is negative xc relative to B, which is a quantity that we have. We have C relative to B right here. We don't have xc relative to D, we have negative xd relative to C. That's the quantity that we have here. And we do actually have xd relative to E, so that's nice. So that stays positive. And now on the right-hand side, every one of these quantities is known. Every one of those is given to us in the problem statement. And that's how I like to do a lot of these physics problems, is that I'll come up with an algebraic solution that's written only in terms of known quantities. All right, so negative xb relative to A is +5. Negative xc relative to B is -2. Negative xd relative to C is -13. And positive xd relative to E is -7. Go ahead and again check the problem statement and make sure that I've plugged in these values correctly. Add those all up, and we get -17 feet, which according to our coordinate system is 17 feet to the left. So I'm going to put a box around this. This is perfectly acceptable as long as somewhere on the page I see that you've specified your positive x direction to the right. But you could write 17 feet to the left. Or just 17 feet left. All right. A brief word about net displacement. Much of physics is about motion, and we are therefore concerned about the change in displacement over a time interval. So we define the net displacement as the final displacement minus the initial displacement. We denote that as delta x, and that's equal to x final minus x initial. This pops up all of the time. You'll note that I've dropped the vector signs. You can draw them in if you want, but I'll say at this point in the video, I'll just mention that we sometimes drop vector signs, but only for 1D motion. It just gets a little tiresome to write them in all the time, and so in some of the later videos you'll see that I omit the vector signs when we're working in one dimension. Note that the subscripts play a different role here than they did when we discussed relative displacement. Net displacement, so x final is just the final displacement, and x initial is the initial displacement. We don't say what it's relative to, but what's nice is that as long as it's implied that these are both relative to the same position, and so when you subtract them, you actually just get a quantity that doesn't even need subscripts. So that's very nice. And net displacement is particularly important when defining velocity, and that's going to be the subject for our next video. So let me show you a couple of examples, or just one example with net displacement, and I'll round out this video. All right, so here's our example. A car drives directly north along a straight road. So it's in one dimension. If it ever turned east or west, then it would be a two-dimensional problem. After 1 hour, it is found 40 miles north of its starting location, and after 2 hours, it is found 100 miles north of its starting location. Find its net displacement over A, the first hour, B, the second hour, and C, the 2 hours together. Okay, so what I'm going to do is, let's see. Yeah, let's just do this piece by piece. So for part A, we want the displacement over the first hour. And so x final, the final displacement, is equal to x1. And that's 40 miles. And x naught, where it started, was 0. One handy thing, you actually don't need to write miles when the quantity is 0. You can just say it's 0 length. It doesn't matter if this is miles, centimeters, light years, it doesn't matter what units you use. Okay, as long as the quantity is 0. Delta x is therefore x final minus x initial. And that's equal to 40 minus 0. And that's 40 miles. Well, that was practically given to you in the problem statement. The problem statement said that after the first hour, it was found, after 1 hour, it was found 40 miles north of its starting location. And so there's your net displacement over that first hour. Let's do part B. Find the displacement over the second hour. This one's not trivial. This one's really the only really non-trivial of the 3 questions that were posed to us. X final is equal to x2, and that's 100 miles. X initial at the start of this second hour is actually x1. So I really apologize. We use the subscript 0 to denote initial, but I'm using these numerical subscripts to denote which hour we're looking at. So x1 is its displacement after the first hour, and x2 is its displacement after the second hour. And so notation's a little bit confusing, and I really can't help that much. So x initial is x1, and that was 40 miles. It was found 40 miles north of its starting location after the first hour. And so delta x is equal to x final minus x initial. Where did it end up? 100 miles north. Where did it start? 40 miles north. And so it's a net displacement over the second hour of 60 miles. And bad me, going all the way back to part A, and for this entire problem statement, I didn't pick a coordinate system, so I'll specify that now. Plus n. North is positive. All right, let's finish it up. Part C. X final was x2, which was 100 miles. So it ends up at x2. Part C was what's its displacement over the 2 hours. X initial was where it started, which was at 0 miles. And delta x is equal to x final minus x initial. And that's 100 minus 0, which is 100 miles. So over 2 hours, its net displacement was 100 miles. Very simple, I think. Should be easy to work with. It will get conceptually a lot trickier when we deal with velocity. And like I said, that's going to be the subject for our next video. So I'll see you then. Bye-bye.